Everyone, September 21st. All right, let's get this one going. Is subsequence given two strings, return true if S is a subsequence of T, false otherwise. Subsequence is a string is formed from the original by deleting some of the character without disturbing the relative position. For example, AC is a subsequence while AC is not. Okay, so basically we go, okay, what is this follow-up? Suppose there are lots of incoming S where K is largely equal to. If you want to check one by one to see if T has its subsequence is this in this scenario, how would you change your code? All right, let's deal with the first one first. So S, this is a T, right? So basically we just check one by one, and then we have two pointers, right? I have 2 pointers, and then when they match, move forward. This one move forward, match. Yeah, so it's 2 pointers for solving this. Fairly simple. But have to consider the follow-up. I'll deal with follow-up later. Let's deal with this one first. So int I equal to 0, int j equal to 0, right? And then we say while which one will go first? Well, we'll scan. Well, I is smaller than s star length and j is smaller than t dot length, right? We say if s dot char at I is equal to t dot char at j, right? If these are equal, then I plus plus. And then if not equal, then we don't. So we get out, then we turn. So if we match, then I shall equal to s dot length. Yeah. I think that shall do. Wait, hold a second. What is this? Oh, I didn't terminate it. Okay, let's see if this implementation is good enough. Yep. So it's not that hard, right? It's an easy problem. Is subsequence 392. Alright, let's try to deal with the follow-up. So the follow-up is if we have a lot of S, right? A lot of S. And how would you do? I mean, we can, let's say, maybe put everything into a set. I can try that, right? We can try that. Or That's the only thing I can think of is put into a set. Yeah, because the possibility is not that much, right? Because a t is 10 to the 4th. Yeah, essentially there's a lot of possibilities. Whether it is a subsequence, yeah, you have to check, right? If it's not in there, you have to check. If it's a duplicate, yeah. Or maybe like can like do something like DP-ish. I don't know. So let's see, what do people say for follow-up? What did the follow-up? Okay. Hold a second. Since we use t-model time, you can pre-compute t-string to jump to the next index faster. What do you mean? We map this to the index. We map t. Okay. Find next index. So every time we go through S, and then we go for the next index. Ah, I see what you're trying to do. So you don't have to go one by one. So you know your next is C, so what are all the possible indices, right? And then you have the current index, your binary search to find the closest, right? You find the closest. Yep, that's good. Yeah, you make everyone a little bit shorter. That was good. Okay. That's that. All right, let's go back to this one. So wait, hold on. No, I want to do this. I read the solution yesterday, so let's see if we can recode it. So basically, the ideal is we have two arrays, right? We have two arrays. We have the array 1 and we have array 2, okay? And then they have like these. And then they have like these. So the ideal is we want to find a position. We can call it partition position, okay? And we find a partition position such that the total number, like if we have this count, so like it doesn't matter even or odd, right? If it's even, then we want length divided by 2 on the left, okay? If it's odd, we can also say we want how many? We want length, depending on which one you want, right? So let's just say it doesn't include, let's say these belong to the right, right? This partition point belong to the right. So yeah, we want half on the left, and let's just call it also half, all right? Let's call it half. So if it's 4, we want 2. If it's 5, we want 2. Then we want to find the maximum of this. So that's what we want, to make sure this, because this is smaller than this, right? So we need to make this is also smaller than this. And then we want to make this is smaller than this, and this is smaller than this. So the condition that this is smaller than this is if this value is smaller than this value, right? This is smaller than this is if this value is smaller than this. So, right? So then we have If we call this 1, right, this is nums1, nums2, then we have a max left 1, min right 1, max left 2, and a min right 2. And we have a start, right? So what we want to make is, the first one make is this one need to be smaller than this one. So if this is bigger than this, that means we need to move this direction, right? So if this is good, then we need to make sure this is smaller than this, or this need to be bigger than this, right? If this needs to be bigger than this, if this is not, then we need to move this to the right. So we just go back and forth until we find a position, right? Until we find a position that it works. And we honestly only moving on this side. We don't have to move on this side. We just pick a middle point. It doesn't really matter, right? It doesn't really matter. We just pick a middle point and then we move this. Because the worst case scenario, let's say all of this is smaller than this, right? Then we simply just wait. Hold on. Do we need to move on the bottom? Well, I think we don't have to move on the bottom. Well, the reason is, yeah, let's say this is big, right? This is big, and these are all small. So we just keep moving until we get out, right? Now, if we get out, then, yeah, then if we get out, like if this position get out, then this will definitely append to the front. Then we can theoretically calculate it. Or if this one is very big, this one's always bigger than this, so we keep go, and we go all the way to the front. How's that gonna happen? If we go all the way to the front, right, say this is still bigger than this. If this is still bigger than this, yeah, how's that gonna work? This is still bigger than this. Huh. I guess I haven't fully understood the solution. All right, let's go back to take a look. Yeah, we have partition A, partition B, right? It's all fine, I understand that. You're always moving partition A. So what if max left A, if partition A is equal to 0, right? Then this is being maximum min value. Max A becomes min value. So if max A is min value, oh, partition B moves with it. Ah, that's this part I forgot. Yep, partition B move with it. Okay, partition B move with it, which means if I go this one to the front, then this, yes, this one will go out, will go back. Ah, that's the point. You move the partition here, this partition will move as well, because the whole point is maintain this and this to be the same, to be the length divided by 2. That's what it is about. Yeah, then when this go all the way here, partition B will go all the way, some position, right? Some position, and this will be all the way here. And and this will be larger. Let's say this is still larger, right, than this. If this is larger than this, that means the whole thing is going to be large. Then we just need to, and then this is the target, right? This is the target. We also need to make sure once we start calculating, because it's these four, right? These four is what we need. So if it's even, that's going to be the bigger of these two and a smaller of these two. If it's odd, then it's going to be the bigger or smaller of these two. Smaller. It'll be smaller of these two. Okay. All right, let's give this a shot. So this is the official solution. This is the official binary search solution. We create two partition. We use two partition points. I for nums1 and j for nums2, such that I plus j equal to nums len nums1 plus len nums2 divided by 2. Right, it's very important. Right. Then nums1 I minus 1, nums1 I, nums2 j minus 1, and nums2 j becomes the four, right, the four values surrounding the median point when nums1 I minus 1 is smaller or equal to, right, nums2j and nums2 j minus 1 is smaller or equal to nums1 I, right? If either does not match, we move I accordingly, right? We move I accordingly, and subsequently, right? And subsequently, j will move as well. Right? Eventually, we will arrive at the proper I and j position, and from there, we can compute the median. Okay, now is the implementation. So I have int j, int half shall equal to nums1 dot length plus nums2 dot length divided by 2. Okay, I have int I equal to and then we need to make sure one trick is that we make nums1 always the smaller, always the shorter of the two arrays, such that the runtime can be optimized. Okay, so I have nums1. I'm going to say int short nums1 dot length is smaller or equal to nums2 dot length nums1, otherwise nums2. Okay. Oh, it doesn't work? I can't assign? I cannot assign it. That is a bummer. I guess he cannot assign. Really? It's just a pointer. I cannot assign. And how do you do? How do you make sure? Oh, ha! That's a good trick. That is a good trick. Yep. Larger than nums 2.length. I didn't think of it. Nums 2, nums 1. Wow, that's a brilliant trick. Alright, now we have a half. Now int I shall equal to nums 1.length divided by 2. Right. So we just pick a halfway point. Yeah, it doesn't really matter. Int j shall equal to half minus I. All right, because I plus j is equal to half. So we pick one. Yeah, we just pick this. Okay. Then what do? Well, we'll go until we satisfy, right? That's just while through this. Okay. We are going to go the, let's say, int min max left 1, int min left 1, min right 1, int max left 2, int min right 2. Okay, so we can say max left 1 shall equal to, right, nums 1I minus 1, right? But if I is equal to 0, which means we have to check. If I is equal to 0, then we can do integer dot what? So we want this to be small, right? So we can say min value, otherwise this. And min right 1 shall equal to nums I. And then max left 2 shall equal to j equal to 0. Well, honestly, it's not gonna happen. Right? I don't think it's gonna happen. So we can just do nums 1 to j, and the min right 2 shall equal to nums 2 j. Right, this should be j minus 1. And this, yeah, we have to say if I is equal to what? Nums 1.length. If it's equal to that, then we need to use a different value. Right? So we go, all the way towards the right. Because everything is too small. No, everything is, because it's too big, then we move it. It's too small. So now we move all the way to the right. Then in that case, right? In that case, you know what? I think this is max. This is max, and this one is min. So we say integer dot min value. Okay. Nums 1. Okay, so I have all these. You know what? Let's just do 4 lines. All right, now we're gonna check. Right, we're gonna check. We say if max left 1 is smaller or equal to min right 2 and max right no, max left 2 smaller or equal to min right 1, then this means we found it, right? We found it. Now it's going to be, we say if we can say we took a Boolean value is odd, so it'll be nums1 dot length plus nums2 dot length mod 2 equal to 1. All right, so we say if is odd, then we're going to return the math the minimum of min right 1 and min right 2, right? Yeah, because it's a partition, it's on the right hand side, so we need to find the minimum of the two. Else, right? Else we should return the something plus something divided by 2. Right? So it's gonna be math dot maximum of max left 1, max left 2, plus math dot minimum min left plus no, not plus, min right 2. So that's that. Else if, right? Else if, let's say max left 1 is larger than min right 2. So max left 1 is larger than min, so it, I need to move left. So we can say maybe we will just do yeah, where is the binary search part? Where's the low and high? We need to have a low. Right, now we can say int I and j. We can say I equal to low plus high divided by 2, and j equal to half minus I. Right? So now I we can say equal to now I high shall equal to I, right? But I is not working, so I minus 1. Else, so this else will be max left 2 is larger, or min right is smaller than, so too small, so we need to move to the right. So we said low shall equal to I plus 1, right? And then go back up, we try it again, and eventually turn 0. So this shall not reach, right? We shall not reach here. Okay. Why is one not right? Unreachable statement. Oh, really? Unreachable statement. Because it says, well, true. I can say low small equal to high. That shall work. Yeah, not sure. Let's see. This one works. Index out of range. max left 2. Interesting. Hey, what if we hit this one? I guess we have to worry about this one too. So what if j is equal to 0? Yeah, I didn't consider that. What happens when j equal to 0? Well, when j equal to 0, that means when j is 0, that means we have exhausted everything. So max left 2. So what happens when j equal to 0? So basically this means I keep going right? I keep going right, which means the min right one is always smaller, right? So keep going, keep going, keep going, keep going, keep going, and then boom, all the way to the right. Okay, so when that happens, the max left 2 shall become a what? Yeah, this is too small, right? Main right is too small, too small, too small, too small. So which means but I think the point is this won't happen. Oh, if it's even, right? It's the same length. Yeah, it will happen. It will happen. So what we need to do is max left 2 should be smaller or equal to. So what we can do is do exactly the same thing. We say if j is equal to 0, okay, then it would be integer dot it's actually, I think it's going to be minimum value. All right. Because we want max left 1. If that goes to 0, which means it's too big, right? It's too big, too big, too big, too big, too big. And then all of this is big. All of a sudden we have the first half, right? Then when we do this, we'll say max left 1 is smaller or equal to min right 1. And then we'll take max left the maximum of this and this. So I think this should be min. And this should be max. Okay, so this one will be the same. We say j equal to nums 2 length, right? Then integer dot max value. Otherwise this. So which means when I is equal to 0, so the first array is too big, right? Then we do this check. This check has to pass. So this is smaller or equal to, yeah, this will pass. And then left is a pick a max, so this one will be eliminated. Okay, so the same thing, right? Min right. If the j all the way go to the right, what happened when j go all the way to the right? That's when I go all the way to the left as well, right? I go all the way to the left, and then j go all the way to the right. Then, yeah, I think this probably is right. Man, if it's really an interview, that is gonna struggle. We're gonna struggle on this one. Yep. No. Tough. Very tough. O log minimum m n. Yeah. These 4 statements are very tricky to get right. Okay, so that's that. Yeah, this one yesterday. All right, we consider this one done. Let's just do more JavaScript. Yeah, for fun. Give an array of asynchronous functions. Write a new promise. Each function in the array accepts no arguments and return a promise. All the promises should be executed in parallel. Resolves when all the promises returned were resolved successfully. The resolved value of the promise should be an array of all the resolved values. The promise should resolve when all the asynchronous functions in the array completed execution. Rejects when any is rejected. Yeah, basically just promise.all. Okay. Can we implement it using promise.all? Actually, I don't really remember how promise.all works. Okay, this one is. Yeah, I'll check this one. Let's just close this and just call promise all. Okay. So I have promise, another promise, another promise, and then promise all dot then dot value. So if I use promise, then I can say promise dot all, and functions is an array, so I can do functions, right? Promise all dot all functions, right? And then what do I return? Output resolved 5 should be dot then, right? Dot then values. Oh, maybe we should just return this. Is this is how we're supposed to do, right? Promise.all, promise.all. Oh, I think they disabled it. Oh, hold on, no, they did not disable. I think I did it wrong. No, I think you didn't. You have to dot then vals Yeah, I think this probably worked on the all dot catch. Maybe this one should work. I don't even know how to solve it within promise.all. Return a new promise. Return a new promise. So hold on. Let's say we'll return a new promise. Okay. And then we have reject. Now we have a resolve and a reject. Right? And we can say resolve vals then dot catch error, reject error. Maybe this is the way to go. Is that the way to go? New promise. Oh, it doesn't work. I'm confused. A new promise. Function is this. Or did I pass this one wrong? No, it's, yeah, it is a... Oh, you have to execute it, right? I think I didn't execute it. So, oof. So we need to find the return value and put the return value into it. Okay, so functions.map. This, we just call it that. That should be right. Yep. Then in this case, I think we can just do it this way. Return this. Nice. All right, lazy way. Got it. No way. No way this is wrong. Come on. Cheating. Cheating way. Using promise.all. Alright, now we have to try to figure out how do we do it without cheating. Honestly, I don't know. How do we have them go in parallel? I don't know. How do you do in parallel? The first one, start, setTimeout. I don't know. How do you do promise in parallel? Can we have some insight? Ask JavaScript. Execute promise in parallel. Yeah, it's all about .all. Pending, fulfilled, and rejected. Sequentially, you just chain them. Okay, parallel. We start and process multiple processes simultaneously. Okay, let's just see. This one is sequentially, right? So task 1, task 2, task 3. We do task 1, then task 2, then task 3. Yes. So are you saying we just do task 1, task 2, task 3? No, you're using promise.all. That's not what we want. Yeah, it is concurrent. Maybe you can use any. It says just don't use all, right? So, I mean, race is one of them come out. Any, I think any is, what's all settled? Oh. What's the difference between all settled and all? Not dependent on one another to complete successfully. Oh, this one will wait until everything is settled. I will wait for everything. It's not what we want. Any is a single promise. This return promise fulfills when any of the inputs promises fulfills. Any. And it rejects when all gets rejected. Yeah, I don't really think that's the one though. Then how do we implement this? There's no hint. I have no idea. Yeah, how do we emulate? await. How is this? How is this? For each, we create a function. We will try. We will await. But do we call this function? Oh, wait, hold a second. How does this work? Resolve count. If resolve count equal to this, then you wait, hold on. What the hell is this magic? A resolve count. A resolve count. I mean, it's on the outside. So basically, each time you add, every function gets affected. And then once the last one gets resolved. So like if, huh? So we return a promise, okay? So inside this promise, we say each function will do this, right? And then we'll wait it. We'll wait. And then we do the next one, do the next one, do the next one. So we, okay, so we using this, every function gets weighted. And then the first one gets out, plus plus. And this one is false, right? Because it's false. So shouldn't that function just be done? What the hell? Array of promise return functions that return a promise that resolves to an array, retaining the order. So how does this resolve work? So when this is the right, so this promise we try to resolve. So we try to call this function, right? Are we constantly polling it? Constantly polling it? Oh, ho. You resolve this res. Oh, I thought you resolved the subres. Oh. What? That works? Is no like racing condition? My JavaScript is weird. It's so weird. What the hell? Okay, so alright, so we try to resolve every single function. So that's how you do a parallel. Okay? So you do a parallel, I mean it's not really parallel, it's concurrent.
So you call the first function, right? While it's being resolved, you call the next function, because every time it's getting resolved, I think it pushes it to some place else. It's waiting for the return value, right? Because of these states, you have pending and fulfilled. Yeah, so what I think is every time you try to resolve it, right, you call it await on a promise, then it's pushed to a wait queue, right? It just pop out of the current stack because it needs to be waiting, so it will continue doing the next one. We'll do the next one, do the next one. And whenever it's ready, right, it will send back like a interruption, right? It will send something back to say, okay, I'm ready, and then it gets resolved, right? It gets resolved. So concurrent in this case is equivalent to if you just call this await multiple times. You call await, you call await, you call await, and every time you call await, it will await. So yeah, so basically we call await, right, on we call await on all of them, right? We call await on this, and then this current code gets paused, but then the next one gets executed, the next one gets executed, and they all get executed. So everybody is wait for some IO to do. Whoever goes first, we put the result in, right? And then, we do this and this. So the last one gets resolved, gets to do this. Oh my god. Yep. It rejects as soon as it rejects, otherwise it waits for everything. Yeah, then it just immediately rejects. Uh-huh, yeah, that's what something you can do. Or you can say, yeah, or you can use this. Encounters the wait keyword, just like setTimeout. Doesn't halt. It pauses execution of the current function and allows the event loop to continue, executing the next iteration of the loop. When we reach this, it doesn't block the entire for each loop. It merely pauses the execution of the function and proceeds with the next iteration. This gives us an illusion of concurrency, as all prompts appear to start almost at the same time, or resolve or reject whoever they're ready. That's true. Event-driven non-blocking. Event-driven non-blocking model. Yep, good explanation. Oh, good. It's very good. Oh. So event-driven, right? JavaScript is event-driven. So there's nothing is blocking. setTimeout does not block. Await also does not block if there's another one waiting to be run. All right, so this is right? We need to return a new promise, resolve, reject. I got this part right. Okay. And then yeah, I think we can say if function the length is equal to 0, we just immediately resolve with an empty array. Okay. Should we also return? Do we also return? Yep, we do return. Otherwise, yeah, let res equal to, no, res can be const. New array. Functions.length. Fill. I'm guessing, I'm not sure about syntax. And let num resolved. Then functions dot for each. Function and index. Async, right? Has to be async. Try await function const current res. We can actually just say res index equal this num resolved plus plus. If num resolved is equal to function dot length, we'll resolve the res. Okay. And catch reject. Okay, let's give this a shot. Coded by myself. Oh, nice. Good one. Yeah, I need to mention. This is completely from the official solution. The key point, the key take-home point is that await is non-blocking, just like setTimeout. Thus, we can call await on an array of functions without the for each on the functions array for each on the array of function being blocked. This creates an illusion of concurrency, of parallel. It is concurrent. It's a good one. Okay. All right. That shall be it. All right, that shall be it for today. I'll see you guys tomorrow. Adios.